Good afternoon. Welcome to Happy Maths Hour for today's third edition of Pythagoras Theorem. We have the amazing Tony Bearden here to talk about it, and I shall be asking a gazillion questions. Tony.
Less of the amazing.
You always poo-poo me when I say you're amazing. You are amazing.
Well, we're sort of going to go back 200 years, not 2,000 years or more. And we're going to sort of just chat a bit about how it was in the 1800s, the 19th century, and how much maths and science came about then. Now, you'll see on this slide, Henry Perigal. We'll talk about him. He was an eccentric Victorian gentleman and a mathematician, astronomer, but only I shouldn't say only, but an amateur one who did some really very good work. And as you see, the picture on the screen is what I call a proof without words. We'll come back to it later. So just to remind everybody, but I think you don't need reminding, if this is the first of these Pythagoras story Happy Maths Hour that you've attended, then I'm going to tell you that the theorem was known in 1,000 years before Pythagoras, but it's named after him. And what is it? It's that the area of the square on the hypotenuse, c squared, is the sum of the areas on the two other sides, which we'll call the legs. That's it. That's all it is. Now, last time, if you look at this slide, you'll remember we did a jigsaw puzzle, or we talked about a jigsaw puzzle, which has these 7 pieces. And the question was, fit 5 of these pieces together to make a square, and you've got the 5-piece solution there, and fit 6 of these pieces together to also to make a square, and you've got the 6-piece solution there. Actually, there's more than one 6-piece solution, but and we talked about the variations last time. But what we say amounts is exactly, same thing's going to apply to every form and every shape and every variation of the solution. So do you think this is convincing and even accessible for 12-year-olds, Caroline?
I do, because it's not about Pythagoras, it is simply about shapes.
Yes.
And if you don't mention Pythagoras, you just look at triangles and squares and do. So the way this works is that you place the 5-piece puzzle inside that square, as I think Tony's got an animation there, and then you remove the 4 triangles, and you do the same with the other one. You remove the 4 triangles. You see that the area is the same, that a squared and b squared take up the same area as c squared, because the rest of it is taken up by the same 4 triangles. There's nothing technical about that at all. You're just talking about squares and triangles.
Yes, and it isn't algebraic, as Caroline says. It's all about shapes and areas, which they learn. The children learn about in primary school.
Yeah, about 8 years old, they learn about area.
So, and the other thing that they can do in the class is to not just to make this with one puzzle, but to make their own puzzle with different triangles. So, I mean, the 4 triangles must be the same, copies of each other, but if different groups in the class start off with different shaped right angle triangles, the blue triangles, but do exactly this, everybody will see that the same argument applies whatever the angles are in their particular right angle triangle.
It'll just be that the squares are different sizes, but the proportions will be the same.
I'm not sure about the proportions, but the layout, yeah. Well, the layout will be the same.
You'll have the same pattern. You'll have the same puzzle.
Exactly.
The lengths will be different.
Yes, and I mean, for example, if you had right-angled isosceles triangles with angles of 45 degrees, those corners of the pink square would be at the midpoints of
Right. Yes.
the edges. But
Yes.
but the point is that if different groups have different blue triangles, all their set of 4 will all be the same, but they've got different ones. My group will have a different one from your group, Caroline.
Yeah.
And then the children can see that whatever the right angle triangles are, got 4 copies. And this, the fact that the pink triangle must be the same area as the green and yellow put together must be the same, whatever right angle triangle they start with.
So I think, would relationship be the right word? I'm just thinking, because the formula is a squared plus b squared equals c squared. So that's a relationship between them, or
yes,
yes.
no, yes, it's a statement of the theorem in algebraic terms, isn't it?
So in other words, whatever they do, the relationship between the triangles and the squares is going to be the same for everyone. It's just that the numbers will be different.
And the beauty of this is, as you said, this is how you started talking about it, that it's all about shapes and not just about number. And the worst way to teach Pythagoras is, this is the formula. If you know A and C, how can I want you to find B. You've got A as 2.5 and C as 3.7. What's B? That's the worst way to teach it, And what we want is the children to discover this themselves. Now, how about this? Have a look at it. I'll say nothing while you look.
So I've just seen that pattern that we just had. I've just seen the square. You're just alternating between the two. So just by translating those triangles, you're alternating between the two puzzles.
Isn't that beautiful?
It's gorgeous. It's fantastic.
Yes. And that is another version of the 6 pieces, 6-piece puzzle, the one on the left. But you can see very clearly in black now the squares that were colored orange and green and pink. You can see them. Yeah, the two, as Caroline says, the 2 layouts are there. Okay, so let's move on to something new, because we did that last week.
But you didn't do the animations. That's beautiful.
No, I've got more animations today. Now
this was absolutely. I looked at this when you first brought it out, when you first showed me, when we were rehearsing, and I was like, I went a bit cross-eyed looking at it, attempting to find how on earth this is a proof of Pythagoras' theorem. Take us through it again,
can you see square? Well, shapes are on top of each other here, which makes it a little bit, as Caroline says. But can you see squares here?
So I could see, I could see the squares. I could see all 3 squares. I could see the big square. I call them the daddy square, the mummy square, and the baby square, because I'm like that. And I really struggle to see all the triangles, but I can see the triangles. I can see 2 outside the big square to the left and below it. And then finally I saw the other 2 triangles inside the big square at the top and on the right.
Yes.
But I wasn't sure how that related to the area. I wasn't sure how that made it a proof.
Well, first of all, you need to have the bottom line a straight line all the way across, so that this is one triangle here. Can you see my cursor?
To the left.
This is the other triangle here.
Yeah.
And these 2 angles, because they're the 2 angles in the right angle triangle, the 2 different angles, not the 90 degree, the other 2, they add up to 90 between them. And so this is 90 degrees here.
Oh, so that proves that it's a square, because of course the first question is, can you be sure it's a square? Okay.
Well, we do know that the sides are equal, the edges are equal in length, because we have got 4 copies of the same triangle here, just as we did in the last one.
So
and just as just as we did in the last one, we those 4 copies can have any angles in the triangle here and here, whatever the right angle triangle, as long as it's right angled, you can fit them into this configuration.
Okay, so you can go everything from a long, long, long skinny one to a nice to
Well, to the isosceles ones with
to the
angles of
isosceles
45
one.
ones.
Yeah,
Yes.
to the isosceles one and the relation. Yeah. So yes, so
And
I can see
we
that. I can
also
see, yeah.
and we also need to say that the straight lines horizontally and vertically are straight lines and perpendicular to each other, because we know that this is 90 degrees because it's the angle in one of our triangles.
Okay. So the thing,
this is 90 degrees because it's the angle in one of our triangles. Right. So we've got this, so this is horizontal.
so that's perpendicular, that's horizontal. So those the angles that look like 90 degrees, we have basically proved that they are 90 degrees.
Yes, I mean, if we did this formally, we'd have to be careful how we stated it, but
Okay.
it can be turned in.
But it's also because the given is that the triangles are all congruent right-angled triangles. Yes. Knowing that, we can derive all the other information.
Yes. Now, the thing about this is that it's been called a proof without words. There's books with a sort of, 100 pages and 100 different theorems and diagrams which show why it's true, and you've just got to see the diagram in the right way. And we're not going to do that quite yet. We're just going to leave people to sit with people, if they've been watching this, to think. Many of you will have already seen it. So I want to digress and talk about the man himself, who was the first one to design that layout for the proof. And
first thing I did was leap to his age. He died at 97 years of age,
which was a very long life for then, and
very
even now.
Long, yeah.
Yes. Now he was a clerk. He worked in a stockbroker's office. He was an amateur mathematician and astronomer, and he produced instruments, mechanical instruments, that automatically drew pretty curves. We'll see some of them. And then he, as far as I can see, he did 2 dissection proofs of Pythagoras' theorem. And it says, I say he did unorthodox ideas of astronomy. They were very clever ideas, but they weren't all 100% correct. Anyway, there he is, sitting in the middle picture there in his sitting room with his flowing white beard. And that's our man. And there's quite a lot of good history on the Maths History St Andrews site. I do recommend it, because if you're a teacher, just adding a little bit of history, when this was discovered, who discovered it, something about the ideas that the children meet in school, just makes it a little bit more interesting, I think. And I love this picture.
I really do. I mean, this man, he looks clearly, he's in his 80s or 90s in that picture. Look at him. And he's in a hammock. And so for that, he's actually got to get into the hammock, and then he's got to get out of the hammock. I'm struggling to do that age 60, never mind in my 80s and 90s. I love this picture.
But do you love the hats, the top hat and the deerstalker?
Yeah. Fashion has changed somewhat.
I mean, sitting in the garden with your top hat on.
Yeah.
Now, this is James Glacier, and I thought I remembered the name, but I couldn't remember what he was famous for. He was very famous. So I think it might be worth mentioning a little bit about him, because he was a scientist, he was an astronomer. And so we're going to talk a little bit about what do you think? Hot air ballooning? Because that's what
I mean, that's of course that's everything to do. Oh no, we're off on a tangent. That's fine. We can do tangents.
It's nothing to do with Pythagoras' theorem. It's just a bit of variety.
Yeah.
So this is a diversion. We're going to talk about scientific life in London in Victorian times, that is in the 1800s, and something about hot air ballooning, because long before we got aeroplanes aeroplanes up into the skies. We got hot air balloons up there, and it's a lovely story. Now, this is all about this film, which is made on Amazon, is actually based on James Glacier's adventure in a hot air balloon. But of course, I think I'm going to shall we show the trailer? It's quite short.
Yeah.
And I would. Can you see it?
Not yet. No, you haven't stopped sharing, Tony. That's why. I think you need to stop sharing because the slideshow. Well, I'll talk about a little bit because I've been researching a bit about this in the meantime.
I'm very sorry. I think you just heard a little bit, but we couldn't manage to show it you.
There's nothing.
Oh,
nothing.
really? Oh, I'm sorry. Okay, well, I'm really sorry about that glitch. Okay, so basically, let me tell you the story. He will tell you a little bit more about the real story, but in the film, I could hear it, you see. I thought you could too, but never mind.
That setting must have reset itself where you have to make it so that you share the audio. So we'll have to do
right. Well, apologies, everybody. We weren't well enough prepared, clearly. Okay, so can you see my screen, my PowerPoint again now, Caroline?
Oh, yeah, no, it never went away, Tony. That's why I thought it was...
Right. Okay, so let's continue. So the story in this video, and I do recommend it, it is, I will put it on the comments on the Facebook page with the this live, the link to this live video. But I'll put the link for the story. Instead of the companion that James Glacier actually did go on this record-breaking hot air balloon flight with. In the story, of course, they made it such that a woman had gone up there with him. And so it's a story about this adventure. So what about it? We'll go on and tell a bit more about Henry, and then we'll go back to the hot air ballooning. So he was called Henry Perigal Jr. because his father lived, who was also Henry Perigal, until our Henry Perigal was 67. So he also went by the nickname Cyclops. I don't know why.
I think because I've looked into the movie since you mentioned it, and I think it might be because he was always had an eyeglass. He was always holding an eyeglass.
Could have been.
That might be it. So he'd be talking to someone and be like, "What?" I don't know. I'm just speculating there.
So that's very possible. It's very possible. So he never married. Our Perigal never married. He had no fixed abode. He lived with friends. So he'd live with a few years at one address with one of his friends, and then he'd move somewhere else and park himself with a different set of friends. And many leading mathematicians and astronomers were his friends. So he was obviously popular. Well, I think he was. I'm not sure how much people liked having him in their house, for long stays. But anyway, that's what happened. And what people did in those days, they had what they called a soiree, which is a party in the evening, and invited people, and the scientific community often had talks about science, or somebody might have played the music and everybody might have, sung along or something. But what Perigal did, he exhibited his instruments that he made, and you see some nice curves on this picture that he got a little mechanical device that drew those curves by going backwards and forwards along the same lines. Now, there were a lot of societies or clubs that people could join, and some of them were even, glorified with the name royal. Now, Royal Institution was quite typical because it was set up in 1799, and it was set up to introduce new technologies and to teach science to the general public through lectures and demonstrations. But it was also a research laboratory, and much of the science that's taught in school these days about electricity and magnetism and optics was actually discovered at the Royal Institution. And so it's amazing.
Tank. I think it was a place where literally, because I go there reasonably regularly, and the library I find is absolutely exhilarating, because I can just imagine all these eminent thinkers and innovators in their day would come together and have discussions at the Royal Institution. Yes, they'd have the lectures, and they would be sharing their thoughts and making discoveries during that same time period. I love the Royal Institution for that reason.
And two very famous scientists, Faraday and Maxwell, actually were based at, and they were the directors of the Royal Institution at different times. And they discovered a lot of, they had science laboratories there, and they discovered a lot of science, and then they would demonstrate it on these Friday evening lectures when people went along dressed as if they were going to go to the opera or something, in all their finery, to sit and listen to science lectures and sometimes maths lectures.
We've got I know who's, I can't see her name, but I know who's watching. She says libraries are wonderful places. So we can say hello to Tennessee. Pigeon Forge, Tennessee. Pigeon Forge, I keep getting the name wrong.
I know that Caroline was actually at the Royal Institution on Saturday doing a masterclass for young people on Saturday. And yes, I've had a bit to do with the Royal Institution in my time. Now, Perigal was elected to the Royal Institution, also to the Royal Astronomical Society, to the London Mathematical Society, and he served on the Council of the Royal Microscopical Society. And for 45 years, he was the treasurer of the British Meteorological Society. And I'm sure that's how he got to know James Glaisher so well, because the rest of this story about hot air balloons is all about meteorology. So they were they were pretty sort of widely, there were lots of wide interests and knowledge in those days. Maths and science have become much more specialized since then. Now, it was the custom in Victorian London that if you visited somebody's house, somebody who of means, you would knock on the door, and it would be opened by a servant, and you would give the servant your card, and then you would stand in the hall and wait, and the servant would take your card to the lady of the house or the gentleman of the house, who would look at the card, see who was there, and decide whether they wanted to really invite them in into the drawing room, or Henry Perigal's cards, he had these three different designs on different cards. The one at the bottom on the right you've seen before. Now, the one on the left is a version of a proof of Pythagoras' theorem, and I'll say more about that later. And the one above is another picture which he had this little mechanical device that would draw that picture and accurately the construction there. So that was those were his calling cards. Now, here you see the basket in which James Glaisher, and Coxwell, who went up on this record-breaking flight, and it flew as high as jumbo jets. So the BBC program about this said as how it was highlighted.
A bit of context here, if it helps at all. Yes, as high as jump. I think it's 37,000 feet. Mount Everest is 30,000 feet. Mount Kilimanjaro is 20,000 feet. Now, at the top of Mount Kilimanjaro, it's very hard to breathe, and you can get disorientated. You get altitude sickness. That's at the top of Mount Kilimanjaro. At the top of Mount Everest, it's even worse. You have to acclimatize. And in aviation, anything over 15,000 feet, you have to use oxygen. This is the aviation law globally. You have to use oxygen above 15,000 feet. If you don't, you can get disorientated and you can pass out. But the biggest problem is you can... a pilot that gets disorientated can crash a plane. It's plain and simple. They can get confused about which way's up and which way's down, and your cochlea doesn't do its job right, and you make false assumptions, make bad decisions, and you crash. So when they got to 15,000 feet, they were, apart from the fact that it was cold, it would have been cold. This is a very, very real physiological issue. So that's how extraordinary what they did is. They went to 7,000 feet.
It is quite amazing.
And it's negative. I mean, if you look at outside an airplane and you see the temperature, because they give you those screens, it's like negative 40, 50 Celsius sometimes. And they went up there. And
there's a picture. You can see Glacier there, absolutely out cold, and luckily his friend Coxwell still had his wits about him, and he had to climb out of the basket in the hot air balloon and climb up to release a valve which had got stuck, because the balloon was shooting upwards out into space pretty much, completely uncontrolled, and twirling round at the same time.
Yeah, it's going round too quickly. So it was spinning and getting higher and higher, getting colder and colder. There would have been, I suppose, if they were still in a jet stream. I mean, I think they discovered the jet stream, at least according to the movie, that they actually found. They made a lot of meteorological revelations from this one flight.
Well, the purpose of it was to collect data for weather, for weather observations, and I think it went slightly wrong, but luckily it ended up safely. They did land safely. So Glacier was taking notes, and at just over 22,000 feet, he recorded that he was having trouble reading his instruments. And at 26,000 feet, he wrote down that he'd lost himself. Well, he obviously passed out. So he was lucky to have Coxwell with him, who loosened the valve, got it back to normal, and then controlled the balloon so that they descended and landed safely.
Extraordinary, isn't it?
And it wasn't long after that, I think it was 1872, that Jules Verne wrote Around the World in 80 Days.
Well, yeah, it was 10 years later that it was published. So it really does feel as though he was inspired to include the hot air balloon. There must have been a lot of hot air balloons around, but one imagines that because Jules Verne is science-based, one imagines that they moved in the same circles if they didn't know each other. So I'd love to believe that this inspired Jules Verne's book, or part of it.
Well, of course, this event we've just described was in all the newspapers, and so everybody was talking about it. And of course, Jules Verne obviously wrote this book over several years, so probably he'd started writing it by 1862 and published it in 1872. We don't know, but I mean, here are some of the sketches and pictures in Glacier's scrapbooks, one of his scrapbooks. He meticulously collected everything he could find, all the newspaper articles and cuttings about hot air ballooning. And they're now in the Cambridge University Library. There's an exhibition there. He recorded popular ballooning adventures and expeditions, and lots of posters advertising balloon rides. So you could go and pay for your tums or whatever it was and have a balloon ride. He drew illustrations of experimental aircraft. So he had a scientific approach to it. So he was Perigal's friend. So let's come back to Perigal's dissection. Now look at it. The colored right-angle triangles are congruent. They're all the same, okay? Just color them different colors for convenience. Now just look at the pictures. What do you see if you remove the two blue triangles?
You've got the larger triangle.
The one you call the daddy.
The larger square, the larger of the three squares.
The larger square, the one you call the daddy.
Square. Yeah.
And I would call that a tilted square. And some children find it difficult to say to identify it as a square, and they have to learn that you can rotate a square around and it doesn't change its shape just because you spin it round, turn it at an angle. So when you remove the two blue triangles, what you see is the square on the hypotenuse. Now then, put them back. Imagine putting them back and removing the two yellow triangles. What do you see?
Well, then you've got the other two squares. You've got the mummy square and the baby square.
Indeed.
You've got the mummy square on the left and the baby square just sitting next to her on the right.
Yes, and you can see that they are the squares on the other two edges, on what we call the legs of the right angle triangle.
Right, the short leg and the medium leg, the non-hypotenuse legs.
If you remove two of the triangles, you get the largest square, and if you put them back, if you remove the other two triangles, you get the other two smaller squares. So they must be the same area.
Oh my goodness, Tony, that didn't click when we spoke about it before. That did not click. It just clicked now. So we're removing the same. These triangles are congruent. They are identical apart from their orientation. So right, remove two, you're leaving the same amount of area. If you remove the other two, it didn't click. Now I see the proof.
But it's exactly the same reasoning as we had with the earlier proof, isn't it?
Yeah, but it's not as easy to notice. But yeah, I see it now. I see it. I see the light.
So there's a whole lot of animations, and I will put this link again in the comments on Facebook. I do like these. You can, if you've got the link, you can play them again and again. And on this one site here, there are many different animations showing you different ways in which you can chop up the diagram and rearrange it and show that Pythagoras' theorem must be true. And I really like it, and I think we can turn them all into puzzles, into jigsaw puzzles, can't we, Caroline?
Absolutely, definitely. They are great jigsaw puzzles. I did one a couple of weeks ago with a rather rambunctious group of 14, 15-year-olds. And even though it's quite hard to get their attention, thank you, Cynthia. Cynthia says congratulations on seeing it. I think it's Cynthia. So it was fantastic because they did get it, they did solve it, and they got enthusiastic about finding other ways of rearranging the squares and the triangles as well. So it's a very engaging activity and very powerful.
Yes, and I think if you show, after they've done it later on, maybe the next lesson, you show them the animation, that sort of, that really drives it home, because Caroline is glibly talking about they. Well, you show every single learner in the class really understood it,
No, not at all. No,
No,
not
no.
at
So
all.
the
They're very
more,
rambunctious, and we didn't get to the point at the end where we were able to come together and
and
really concentrate on
the
it. So
more
that
different,
I'm going to show them that video tomorrow. It's only take a minute. I'm going to show it them tomorrow.
the more different ways you can show them the similar thing, the more they'll get it. And the video Caroline is talking about is the one that we looked at together much earlier on, right at the beginning of this chat. And that's the puzzle. We called it the make squares puzzle that they did. So yes, I just love all these different proofs. And of course, it is possible to, as I said, as you see on this slide, to make this the basis of a rigorous proof, to write down a rigorous proof using the same, steps, but we're chatting informally about it. This isn't meant to be, this isn't meant to be formal maths. This is meant to be just a chat.
But it is, if you want to go there and do the proofs, this will help you. Look at that. Just look at that. That's so amazing. Fantastic. That really does help visualize it.
And so this is the same thing, isn't it? We just saw, but of course the triangles haven't got the same angle. Sorry, the 4 triangles are congruent, but they haven't got the same angles as in the previous drawing.
Oh, really? Oh, so they're just different triangles, but they're right angle triangles. Therefore, it works.
Yes, yes,
right. Yeah.
I think if you remember what the last one was like, there was one
longer and thinner.
Indeed, you could describe it like that. Yes. Yeah. Okay. So the small square was smaller.
Small square was smaller, and the triangle itself had the ratio between the 2 legs, around the right angle was.
Now, what you can see in these pictures is that the striped area is the same in all the pictures. Okay. Right. And in the picture on the left, you have got the whole thing. Okay. And as you saw it originally. Now, in the pictures on the right, the top one has got the 2 upper triangles removed. They were the ones we had in yellow.
Yeah.
And the lower one has got the 2 lower triangles removed, leaving the square on the hypotenuse. So we'll go back, I think, and you can see that this is, as Caroline's described it, these 4 congruent right angle triangles are much longer and thinner than the one on the animation, and that in itself is quite helpful when you show it to a class. Even if you've given them the same puzzle to cut out, so the ones that the puzzle they've been working with, all the triangles are the same. When they see the animation, you can have a discussion about, well, these triangles are congruent and the layout is the same, but these triangles haven't got the same angles in them. They are all right angle, but they haven't got the same angles in them. These are longer and thinner, but it still works.
Yeah.
So there it is. We'll watch it once more. Okay. So here it goes again. It shows it to you twice.
Mesmerizing.
Yeah, I could watch it and watch it. I love it. Okay, so the next, to move on, what about this one?
This one is, it took me actually a long time to see. I could see the small square. It's a bit of the blue and a bit of the green triangle. So I could see that sitting there, but it took me ages to see the mummy square, the medium-sized square, I could see the two rectangles made by the four triangles, but it took me ages to spot the fact that that small pinky lilac-y square sitting on the top there actually completes the medium-sized square.
It is a bit of a distractor, that pink square. Anyway,
Yeah,
it is a variation of well, sorry, it is the same diagram as we've been working on as before, but he's actually chosen to put the pink square in the middle and to show you that you could actually put, and this is what is different about this one, he has put the four copies of our right-angled triangle into the square on the hypotenuse. We hadn't seen that before.
yeah. No.
And what's left in the middle is the pink piece.
Yeah.
Now we're going to have a look at another.
Yeah, and you're demonstrating that the area is the same for the big square as it is as the other two squares added together, because it's the same. The area is the same. All those pieces are the same.
Yeah, but this argument is not so much by removing; it's by noticing that on the right, the daddy, or the tilted square on the hypotenuse, which has area c squared, is composed of four triangles and the little pink bit in the middle.
Yeah.
Okay.
Yeah. It's a different because this is all transformations as well. There's no translations. Nothing's rotated. You notice the yellow one stays the same way. The yellow one and the green one don't move to make the big tilted triangle, tilted square. The light and dark blue ones, they move. They slide along and upwards, but their orientation stays the same. They are just translated to a different position. So I really like this one because of that. That it's it's just moving it around to see, and so absolutely the area doesn't change. You're not removing anything. You're not adding anything. You're simply moving them around.
Yes, and that's right. So what you're looking at is four triangles and a little pink square, and put it in different arrangement, and they must be the same area because they're actually the same pieces. So this isn't an argument about removing anything. It's an argument about noticing that they're the same pieces but in a different configuration, which I think is neat. I think it's very neat. Okay. It is amazing. There's lots of these different proofs of Pythagoras' theorem.
I think this is part of the puzzle with it. It's kind of nice. Did you know when you're looking to solve a puzzle, or you've got an optical illusion or something, you want to solve it, and each one is its own little challenge. It's a bit like that with these Pythagoras theorems. It's like, okay, so where's the proof in this one? And you've got to work it out, and that's part of the puzzle and the fun of it.
Exactly. Now, what about this one? Now, you'll see that one of his calling cards, which we saw earlier on the right at the top, is here. I've got it illustrated in colour, which helps us to talk about it. Now, notice that we have the white triangle in the middle. That's our important triangle, okay? But our carving up here and our rearranging doesn't involve any copies of our original triangle.
No, but it does have four congruent quadrilaterals.
It does. And the way that they're constructed, so do you notice that this edge was, well, first of all, that the mummy square, as Caroline regarded it. So this was the daddy, this was the mummy, and this was the baby. All right, like the Three Bears story.
Oh yeah, absolutely.
So this is cut up into four pieces, okay, all of which have got all of which are congruent, all of which have got a right angle, and then those right angles are popped into the corners of the big square here, and then the smallest square exactly fits in the middle.
Sits in the middle. It's yeah.
So the way
It boggles my mind that people actually created these things and worked all this out.
aren't they beautiful? So this line here that is the one you have to construct. This line, can you see the cursor?
Wait, I'm not seeing it. Oh, that diagonal. Yeah.
That diagonal line.
Yeah.
Now that is parallel to the hypotenuse. Okay.
Wait a minute. Wait. Stop the press. That is parallel. Now, how did I have seen this before. How did I work it out? That is parallel.
Well, it is by construction. You have to construct it that way. But
Okay,
but you have to find, first of all, you have to find the center point of this square, which you do by putting in the diagonals. You're not going to use them for anything else, but you need to find that center point.
So you draw the diagonals of that square, and
yes,
then
just to find the center point.
Just for the construction, just for the.
And then the construction is to draw a line through the center that's parallel to the hypotenuse.
Okay.
So that's one of Euclid's ruler and compass, straight edge and compass constructions.
Okay.
To draw a line.
The other one is just 90 degrees to that.
Yes, and that divides the medium-sized square into 4 pieces, congruent quadrilaterals, as Caroline remarked. Here they're yellow, pink, green, and blue. And then because they've got a right angle, they can be fitted into the 4 corners of the biggest square, the square on the hypotenuse, leaving a square in the middle, which will be exactly the right size for the smallest square to fit in.
So it doesn't matter when you start. So you get the center of that square, and you can draw any diagonal through it. Obviously you don't want one to go right to the vertices, because that's.
There's only 2 diagonals, Caroline.
Yeah, but the point is, you are going to make congruent quadrilaterals as long as they both go through that line and they are perpendicular to each other.
No, but yes, but they must go through the middle of the. No, they must go through the center.
Yes, the center. Sorry, I said the line. I meant the center. So the first one goes through the center. The second one goes through the center. They're going to, as long as they're perpendicular to each other, you are going to get 4 congruent, identical quadrilaterals out of that.
Yes, but you have to have the angles right. So you have to have this line.
Which one?
This
line has to be perpendicular to the.
No, it has to be parallel to the hypotenuse.
Oh my goodness! Yes, I meant parallel. Right. So as that line has to be parallel, which means that the other diagonal is going to be perpendicular to it.
Yeah, and I just think that's a nice jigsaw that we'll produce for people to do, and you can use with your classes in the future, Caroline.
I'm looking forward to doing a whole happy maths hour, like of just demonstrating these things, just playing with them and encouraging other people to play with them and make them and use them. I'm going to get these all laminated, Tony. I've got some foam board as well that I can use. This is I'd forgotten about this proof until you.
Well, we've purposely, spread this out. This story, we're telling it slowly, and we're putting 1 or 2 different puzzles or dissections into each hour, and they'll all be available on YouTube, so you can go and look at them there. And if you want to do it yourself, of course, it's a good idea to look at the video, stop it when you get to the point that you want to see. And yes, and I think what I ought to do, Caroline, is put all these things on the Aiming High website, because that will help people too, and then we can give them a template to print off as well.
But can you imagine you've got spare 10 minutes at the end of a lesson when you're doing trigonometry and Pythagoras and things, and you just hand out different puzzles. If you say you have 15 puzzles, you hand out 15 different puzzles, and they solve one, pass it round, solve another one, and they just literally could have a bit of fun solving puzzles, and hopefully they will actually come to realize, wait a minute, have those realizations for themselves, because it's proof without words.
I think it may take a little longer than 10 minutes, but I think
I don't mean the whole process, Tony. I mean, just let's get the puzzles out, let's play with them, and then another day it's like something you could do as a Friday afternoon activity or something. And the more they play with them, the more that they will get really familiar with and to grips with the Pythagoras theorem, and that it is actually true.
I think the concentration, a lot of teachers just concentrate on, substituting numbers in the formula and given two of the lengths they find the third.
They shall do. They shall do. They sure do. They definitely do.
Okay, so we have just seen some of Perigal's work, eccentric Victorian gentleman in London, and we've now, I mean, it's interesting, I think, we're going back now 3,000 years, people were using these ideas, this Pythagoras theorem, which we call it, although they call it the goo-goo theorem in China. I don't think that's, I think a Chinese person will go, will really hate my pronunciation.
Oh, the pronunciation. Oh, I'm quite certain.
But I must acknowledge that they probably, discovered the theorem independently. But back 1,000, 2,000 years ago, 3,000 years ago, wouldn't their minds have been blown? And indeed, even 200 years ago, wouldn't Henry Perigal and James Glacier's minds been blown by our animations?
Oh my goodness, they would have been that. Yes. Oh, the animations. I mean, they wouldn't have known what to do with themselves. They'd have been jumping up and down, doing cartwheels.
Yes, yes. Well, you see, the thing is, Perigal saw this in his mind's eye. He actually visualized it, right? Now, he, and of course, he and his friends were scientists. He actually had mechanical devices that drew mathematical diagrams.
Yes, I'm sure he would have loved to have created a mechanical device that did the animation.
and they were mixing in the same circle as Maxwell and Faraday, who actually developed the electricity, which made it possible for later on, 100 years later, for the computer to be developed using the electricity, of course. The electricity and magnetism and digital and these components, put them together, and then you can nowadays these animations are to a penny. It's a wonderful world, and things have progressed and are changing fast.
Something they have on the RI is on a £20 note. There's I don't know if I've got one on a £20 note. Is Michael Faraday is on the £20 note?
Oh yes, yes,
with the new ones.
So how about this? Do you want to see it again? Let's see it. Let's see it.
I blinked.
Right, let's go on to it again.
Okay. Oh, there's that. I'm loving that square, and there you go. Hey presto! And again, that's just translations. The orientation isn't not changing at all. It's just they're just the four of them. Oh, three of them are moving.
You've got your quadrilaterals, 4 congruent quadrilaterals. You found those by the construction we discussed, and then you, as Caroline said, you translate them. Translating means you move them, slide them, move them without rotation, without any sort of distortion or rotation from one position to another.
Across, left and right, up and down, but not not rotated. And if you just play that one more time, Tony, you can really see that they're just moving across and up and down.
Oh, you want me to show it again?
I think now that we've pointed that out, I think it would be nice if you can.
Yes, I can. All right. So I need to go back and then come back into it.
There we go. Here we go. So that the green is translating across, up, and the pink one's going down diagonally, I suppose. Each one of them is following a diagonal path. And look at that. Absolutely spectacular. And the dark blue one, or purple, or whatever you want to call it, didn't move at all.
Yes. So there you see what we discussed just now, it animated, and you've got the tilted square, which is a square on the hypotenuse, and that's made up of the black shaded square now is significant. It's the smallest of the three squares, and it sits in the middle. It was red in our previous picture. It sits in the middle, and the other four quadrilaterals are the four pieces that we cut the medium-sized square up into.
And yet that other one with that bright pink one, was it the bright pink one? It had it was actually full right angle triangles. It wasn't quadrilaterals that were surrounding it. So the dimensions to make that happen must be relevant. But so that's another fascinating thing, is how to actually construct these puzzles so that you can create all the different shapes. This one I think we're quite clear about. You've got to do the parallel to the hypotenuse and go through the center. But that other one, I really would like to construct that other one as well, that's made up of four right angle triangles around a little square in the middle. It's lovely.
Well, what is strange about this, and I'd like to know the truth, so I'd like to find a historian of mathematics and get them to do a little bit of digging around for me, because you see what it's my heading here, Dieudonné's construction 1917. Right now, it is the same as one of Perigle's dissections, one of the one he had on his calling card, and it's common. It happens again and again and again and again and again that in maths and science, somebody gets usually his, occasionally her, name attached to when they weren't the first person to discover it.
Yeah.
Okay, and this animation, which I found, I gave you, I showed you the link. I'm going to give you the link. This animation is named Dieudonné's and dated 1917, and yet 50 years earlier, Perigle was going round with the same picture on his calling card.
On his calling card, yeah.
So half of the scientific community in London, at least, must have known that Perigle knew about this dissection, and so
it's not called Perigle's dissection. It's called Dieudonné's dissection construction. Yeah, it's interesting, isn't it?
Isn't it? I think it's just another example. And the trouble is, we had a long discussion of this on that website that you invited me to join, Caroline, recently. And somebody said they had renamed theorems in their lectures when they introduced the theorems. They renamed the theorems because it wasn't fair that these theorems and mathematical concepts were being, somebody was getting all the credit for it when they didn't deserve it. Yeah. But then, of course, the trouble is, if you do that, whenever their students look up this thing in another book, they'll find it's got a different name. So you can't win, really. Yeah. So I think we've come to the end of our hour, and there in the small disc just above the word hour, you see this Dieudonné's.
Oh, Perigle.
Perigal. Is it Judenes or is it
No,
Perigals?
I'm
There you
taking
are.
Judenes back. I'm making it Perigos
That is
construction.
it, right? Now,
It's Perigos
here it
calling card.
is.
That's what it is.
Yes. Right. And here, and in this animation, they call it Judenes.
Oh yes, they do. But it's
And
Perigos. It's forevermore now. Perigos calling card. Forevermore. I'm sure somebody else maybe discovered it before him, but it's thing is, it's, even when a child discovers something in the maths classroom, they have discovered it.
oh, that's true.
So, yeah,
That's true. And
do
I
just
mean, Dieudonné was probably quite innocent. He didn't realize that 50 years earlier, Perigal had been, going around London with this on his card saying to people, "Isn't this pretty?"
exactly, exactly.
Yes. Well, it's 6 o'clock and time to say goodbye.
Thank you so much. Thank you for joining us, Cynthia. It's been a pleasure having you. We've had a few people come on, Tony. Only Cynthia commented, but it's been lovely. And see you next week with more fun Pythagoras. Nothing boring when Tony Bearden's around. See you next week. Thank you.